Good morning, everybody. My name is Wang. I'm a TM staff here at MCL Penn State. Today I want to talk about mapping elemental composition and the chemical bonding at the nanoscale by using TEM. TEM is a technique where a beam of electrons going through a very thin specimen. During the interaction between the electrons and the thin sample, we can collect all sorts of information about the sample. When the beam going through the sample, some electrons will lose part of their energy. We can collect these electrons for use. At the same time, a lot of X-rays can be generated during the interaction between electrons and the sample. We can use a detector to collect these X-rays for EDS. Before we get into details about EDS and EELS, I want to briefly talk about STEM. STEM is the scanning TEM technique which uses a convergent beam or probe, which is different from traditional TEM technique. TEM is using a parallel broad beam, but the STEM is using a probe or convergent beam to scanning through the sample. We can have all kinds of detectors below the sample to form different STEM images. At the same time, we can collect both EDS and EELS signals from every part of the sample when the probe scanning through. First, let's see EDS. Most TEMs we have here at Penn State have Super X EDS system, which has 4 EDS detectors surrounding the sample. It's a very powerful EDS system. We can get a very nice map within just a couple minutes. Here is an example of EDS mapping from a nanoparticle sample. This map was collected all our telos. Collection time was just about 5 minutes. You can clearly see and confirm the composition of these very nice nanoparticles. The material here is PST ferroelectric material. By doing the traditional TEM bright field and dark field and diffraction pattern, we can know there is superstructure or like long-range ordering in this material. By doing the atomic resolution STEM, because the lead is much heavier, so the lead atoms or lead columns will show up in this atomic resolution STEM image much bigger and much brighter. So we know roughly the lead atoms are occupying the A side columns, and the lighter scandium and tantalum atoms are sharing the B side columns. But at this point, we don't really know how they are ordered together. By doing the atomic resolution EDS mapping, if you look at the scandium and tantalum atom maps by themselves, we can see both scandium tantalum atoms, they formed this very nice FCC structure inside of the lattice. If we combine all 3 maps together, lead, scandium, tantalum, we can clearly know the heavier lead atoms are occupying the A side column by itself, and at the B side columns, scandium and tantalum atoms, they are sharing these columns alternately. The material here is oxide complex thin film. Again, by doing the atomic resolution STEM, we can see the atomic structure for both thin film and the substrate, no problem. But for the interface, we don't really know what's going on here. The interface structure here is very complicated. By directly doing the atomic resolution EDS mapping, we can resolve the composition at the interface here, no problem. We can clearly see there is a mixed column of calcium and neodymium, and a mixed column of titanium and gallium at the interface. Then let's talk about the EELS. Same as EDS, EELS can do elemental mapping, but more importantly, EELS can get chemical bonding information from the sample. Here shows the core loss EELS edges from titanium. We can see with different valence state, 2+, 3+, and 4+ titanium edges, they have different energy level, and they have total different shapes. The material here is manganese doped STO capacitor. By doing EDS, we can see there is manganese-rich segregation layer, which is formed at the interface between electrode and the STO substrate. By doing the EELS, we found that by longer annealing time, the valence state of manganese changed from the mixed 2+ and 3+ to mixed of 3+ and 4+. This valence state change from manganese directly responsible for the big improvement of this material's electric properties. Material here is a 2D in boron nitride layer modified semiconductor device. Because the boron nitride layer here is very thin, and also its structure is amorphous, so it was very challenging to directly image this layer. By doing the high MAC imaging, we can roughly see there is this darker layer at the sample surface, and but it's not that clear. Also, EDS can only detect the nitrogen signals from this layer. Boron is very difficult because boron is too light and not much signals from EDS. However, if we just do a very simple EELS line scan across this layer, we can confirm this layer is indeed boron nitride, no problem. We can see both boron and nitrogen edges very nicely. This layer is boron nitride, no problem. Also, the EELS is used a lot in battery material research. The same situation as the boron case in last slide. Lithium is too light for EDS. It's impossible to do EDS for lithium. But EELS, no problem. EELS can detect lithium signals easily. Here shows an example. We were able to identify different lithium compounds by doing the EELS in SEI layer in this new battery material. In this last slide, I want to show for the very first time, right now we are able to do EDS and EELS at the same time here at Penn State, or our brand new Spectra Ultra TEM. Here you can see we can collect both EDS and EELS elemental maps side by side from different elements, which is very exciting. that's all I have. Thank you so much.